Good morning, everyone. This is Jeremiah recording from my backyard on a very sunny summer day. Um, Before I begin, let me say how disappointed I am that I'm not going to be able to be there to hear about your final projects. So many of you are doing such exciting, interesting work, and I sincerely look forward to reading about how everything turned out in your final blog posts. But moving on. Just to review, I work as an archaeologist in the Valley of Oaxaca, Mexico, which is site to one of the earliest and most enduring civilizations in the New World, the Zapotec state. My research focuses on pottery production and exchange at the height of Zapotec civilization, when we suspected the emergent secondary centers, such as Dainzumacul Xochitl and Halieza, were beginning to break away from the capital at Monte Alban. The primary question we are trying to address with this research is to what extent were these communities still trading with each other during this period? To answer this question, we analyze the elemental composition of ancient pottery and compare this to similar data for clay samples that we have collected from road cuts, stream banks, and anywhere else we could find exposed clay deposits. As you can see in the map to the right, the geology of the area is quite complex, leading to stark differences in clay chemistry between different parts of the valley. The majority of our samples, however, were collected from alluvial sediments on the valley floor, where we know much less about how the mixture of parent materials affects clay chemistry. This is important because we cannot sample every clay deposit, but wish to identify possible production locales between our sampling locations. Our questions for this study are twofold. First, how do concentrations of individual elements in Oaxaca clays pattern spatially across the region? And second, how are concentrations of these elements related to environmental factors such as parent material, soil development, and the transportation of sediment through alluvial systems? Because this is an exploratory study, the present analysis is limited to 5 elements measured for 137 clay samples from the eastern Tlacalula branch of the valley. These include aluminum, calcium, sodium, potassium, and iron. A key assumption of this study is that one of the fundamental drivers of clay chemistry is geologic parent material, but for most of the valley floor, this is simply mapped as alluvium. Yet when you walk around the valley, you can often see clear differences in lithology from field to field. In this photo, for example, the purple-gray soil in the foreground is derived from andesite, while the redder soils in the distance are derived from older metamorphics. Clays from the red soils have much higher concentrations of iron and other metals than those derived from andesite, but this is not reflected in geologic maps for the region. Fortunately, differences in sediment lithology can be easily detected using remote sensing. This study relies on 13 bands of aster imagery covering the Tlacalula Valley from a beautiful cloud-free day in June of 2001. To reduce the dimensionality of this dataset, I used the principal components analysis to transform these 13 bands into 4 new variables describing the primary axes of variability in the data. This is a false color image of the second, third, and fourth principal components, showing stark differences in spectral measurements across the valley floor. Presumably, these reflect differences in sediment lithology. However, clay chemistry is a product of both parent material and soil formation processes. In an attempt to account for the latter, I included 3 additional variables derived from an aster DEM in my analysis: elevation itself, slope, which is a particularly good proxy measure for the differential processes affecting alluvial and residual soils, and flow accumulation, which provides a direct measure of location in the valley stream network. My specific hypotheses regarding Tlacalula clay chemistry are threefold. First, concentrations of individual elements will be spatially autocorrelated due to their association with particular parent materials. Second, the elemental composition of clay deposits will be strongly conditioned by geologic parent material as measured through spectral reflectance and emissivity in the aster imagery. And third, the elemental composition of clay deposits will be further affected by soil development and alluvial processes as measured through elevation, slope, and flow accumulation rasters. My null hypothesis, of course, is that clay chemistry will be poorly predicted by both aster imagery and DEM-derived variables. To evaluate these hypotheses, I will use 3 statistical methods. First, I will use Moran's index to assess the spatial autocorrelation of each element. Second, I will use exploratory multiple regression to identify an optimal combination of global predictor variables for each element. And third, I will use geographically weighted regression to examine local deviations from global fit that may result from non-stationarity in the data. The results of our test for spatial autocorrelation are pretty straightforward. Moran's I-values are highly significant for each of the 5 variables, confirming our first hypothesis that concentrations of each of these elements are spatially autocorrelated. Exploratory multiple regression is a brute force method for identifying optimal combinations of predictor variables in complex multivariate data by assessing the relative fit of all possible combinations of variables. Shown here are the final models selected for each of our 5 elements. I can't go into this in much depth here, but there are 3 important things to note. First, all elements are best predicted using a combination of aster and DEM-derived variables, confirming that both parent material and soil formation processes influenced local clay chemistry. Second, each element was predicted using a different combination of variables. And third, while each model is statistically significant, they are relatively weak predictors of each element. A possible reason for the poor fit of the exploratory multiple regression models is that they carry the assumption of spatial stationarity, and yet we already know from our Moran's eye test that these data are spatially autocorrelated. Geographically weighted regression is a good post hoc test for evaluating whether local deviations from global fit are an issue for ordinary least squares models. Shown here are quasi-global measures of fit for geographically weighted models relative to those of the final least squares models selected through exploratory multiple regression. Each shows slight to moderate improvement over its least squares counterpart, but what is really of interest are measures of local fit for each element. It would be a bit tedious to discuss each element in depth, so I will just cover a couple here. Results of a geographically weighted regression for aluminum show much stronger levels of local fit on the western side of the study area than the east, indicating a strong lack of stationarity in the data. Results for calcium are remarkably similar. Yes, this is a different map. I discussed this at length in my blog post on geographically weighted regression, but basically what I think is going on here is that both of these elements are highly variable in the west, but have very little variation in the east. Shown here are raw calcium concentrations for each clay sampling location. As you can see, there are a number of extreme values in the west due to the prevalence of limestone in these locations. There are, however, a number of much lower, more normative values just downslope on the floodplain. That is, high variability in both predictor variables and the response. In the west, by contrast, there is minimal variation in calcium concentrations due to spatial autocorrelation, resulting in much lower measures of local fit for this area. We can see something similar in the results of a geographically weighted regression for iron. Measures of local fit are highest in the west and abysmal in the central floodplain of the Rio Salado. Again, I would argue that this is due to the high levels of local variability in iron concentrations in the west related to strongly localized differences in parent material, slope, and position in the stream network. In the Rio Salado floodplain, by contrast, there is little local variability in either slope as a predictor variable or iron as a response, leading to lower measures of local fit in this area. While this is an exploratory study, and the results are preliminary, our work so far suggests that there are significant relationships between elemental clay chemistry, sediment lithology, and processes of erosion and deposition in the Valley of Oaxaca. Furthermore, it shows that these relationships can be assessed using remotely sensed data. While the strength of these relationships varies both spatially and between individual elements, this analysis provides view to the complex factors influencing clay chemistry in the region. For archaeologists, this is significant because it helps us understand the factors influencing the spatial distribution of compositionally distinct clay resources that would have been used by ancient potters to produce their wares in the Valley of Oaxaca. But these methods could be employed in any region. Outside of archaeology, these methods could conceivably be used by anyone interested in how the admixture of different sediments affects soil chemistry at a regional scale. Elements such as potassium, sodium, and phosphorus have enormous importance for agricultural productivity, and this is just one example. One can imagine a range of other potential applications in forestry, botany, geology, and public health. The sky's the limit. For this project, I used a combination of ENVI for processing of the aster imagery, ArcGIS for most other spatial analysis, and JUMP for calculation of non-spatial statistics, including principal components analysis and exploratory multiple regression. I was already familiar with these software, but I would be interested to hear about any other programs or packages that could improve these analyses. I did get to learn how to make a PowerPoint into a YouTube video this weekend, which I've been meaning to do for a long time since I work on eCampus, and I can't tell you how much I'm looking forward to subjecting my students to my droning baritone voice. I'm sorry about all the crazy transitions. I kind of couldn't help myself. Before this project, I was entirely unfamiliar with geographically weighted regression, and after some initially promising results, I was forced to grapple with what these models were really telling me and whether I could in good faith use them to generate predictive surfaces in the way that one would with a strong least squares model, and as I did in a tutorial earlier this term. I ultimately concluded that this would be inappropriate for my data and that geographically weighted regression is better used as a kind of post hoc test for stationarity in a least squares model. But if you're interested, I submitted an absurdly long tutorial on the subject to the class blog, and I hope it's of use to somebody. That's it. Thanks, class. Thanks, Dr. Jones, and thank you, YouTube, for sitting in on this presentation with us. I hope that none of you graduate this year and that I see you all this coming fall. Enjoy the summer break. Bye.